Hello guys, welcome to my channel Algorithm Avenue. In our previous video, we have discussed about the different loss functions like MSE loss, MAE loss and Huber loss that are used for the regression task. Okay, now in this video, we'll be discussing about the different loss functions that are used for the classification task. Okay, among them, our first loss function is binary cross entropy loss. Okay, binary cross entropy loss. In the name itself, it specifies that it is used for the binary classification. It is used for the binary classification. Okay, what is meant by binary classification is when you have two. Okay, when you have two classes in your target variable, then we use binary cross entropy loss. Okay, let's take an example. You have a dataset in which your target variable has two classes, that is dog or cat. Okay, dog or cat. Okay, an image that is given as input to a neural network is classified either into dog or into cat. Okay, in that scenarios we use binary cross entropy loss. Okay, now for this binary cross entropy loss, the loss function is equal to minus y log of y hat minus 1 minus y log of 1 minus y hat. Okay, minus y log of y hat minus 1 minus y log of 1 minus y hat. Okay, this y is nothing but true output and y hat is nothing but predicted output. Okay, y is nothing but true output and y hat is nothing but predicted output. Okay, now when this for the condition that is specified for using this loss function is we need to use sigmoid activation function in our output layer. Okay, we need to use, okay, the condition that is specified for using this loss function is we need to use sigmoid activation function. Okay, we need to use sigmoid activation function where it must be used in our output layer. Okay, in our output layer, all the output nodes, okay, all the output nodes that are in our neural network must have sigmoid activation function. Then our loss function, okay, our binary cross entropy loss function will work effectively. Okay, now let's see a small intuition regarding this binary cross entropy loss function. Okay, now when y is equal to, that is true output of your data is equal to 1. Okay, let's check a data set which has an one target variable y, and among them our first row of data contains, okay, y is equal to 1. Okay, y is equal to 1. When you send that first row of data into your neural network, the predicted output by our model y hat is equal to, let's say, 0.3. Okay, the true output of our model the true output of our dataset is equal to y. Okay, is equal to 1, and the predicted output by our model is equal to 0.3. Now what we need to do is we need to substitute this y is equal to 1 and y hat is equal to 0.3 in our loss function. Okay, we need to substitute this y is equal to 1 and y hat is equal to 0.3 in this loss function. Okay, now, okay, I'm writing it over here. Okay, I'm writing it over here. Okay, now when you substitute y is equal to 1 over here, it becomes minus 1 and y hat is equal to 0.3, that is log of 0.3. Okay, log of 0.3. Now when you substitute y is equal to 1 over here, it becomes 0. Okay, so the entire term becomes 0. So the leftover term is minus 1 log of 0.3. Now let's determine the log of 0.3. Okay, wait a minute, let me calculate it. Yes, log of 0.3 is equal to minus 0.52. Okay, minus 0.52. Now let me substitute the value over here. Minus 1 into minus 0.52. Okay, minus 1 into minus 0.52. Okay, the value calculated over here. Now the loss function that comes out is 0.52. Okay, 0.52. Okay, when the true output is 1 and predicted output by our model is 0.3, the overall loss function of the training example is 0.52. Now what's your task is you substitute different values of 5. Okay, different values are nothing but 1 and 0. Okay, either you substitute 1 or you substitute 0. Now when you substitute 0 here, this term will become 0 and this term will become intact. Okay, unimpacted. okay, this term will become 0, this term will remain unimpacted. Okay, now now the y hat value, must be always from 0 to 1. Why it must be 0 to 1? Because in the output layer, you are using sigmoid activation function. Okay, sigmoid activation function is the rule when you are using binary cross entropy loss. So when you are using sigmoid activation function in your output layer, the value of predicted output will be from 0 to 1. Okay, the value of predicted output but in the output layer will be from 0 to 1. So take different values from 0 to 1 and take two values, either 0 or 1, for the true output, and substitute the values in this loss function and determine the different values. Okay, calculate the different values. Okay, now this is the entire intuition of loss function. Now let's see about the cost function. Cost function is equal to, cost function for this binary cross entropy loss is equal to minus 1 by n, minus 1 by n. N is nothing but the number of samples you are taking. Okay, the number of samples you are considering for calculating the cost function. Okay, sorry, the number of samples that you are taking for calculating the cost function determines n. Okay, so minus 1 by n, minus 1 by n, summation of I is equal to 1 to n, I is equal to 1 to n, and multiplication. Okay, you are doing the summation operator over here, and y log yi hat. Okay, yi hat plus 1 minus yi log of 1 minus yi hat. Okay, now let's say you are calculating the cost function for three samples. Okay, now let's say you are calculating the cost function for three samples, then it becomes minus 1 by 3, summation of I is equal to 1 to 3, I is equal to 1 to 3. First you substitute 1. Okay, so y1 log y1 hat plus 1 minus y1 log 1 minus y1 hat. Okay, then what you do is, for this, okay, for this first term you add another term. Okay, as a summation, as you are running the summation operator, you add another term with y is okay, with I is equal to 2. So next term would be my y2 log y2 hat plus 1 minus y2 log 1 minus y2 hat. And you, as you are taking three samples, as you are considering three samples, the next okay, the next term would be y3 log y3 hat plus 1 minus y3 log 1 minus y3 hat. Okay, now you add up this three, terms for calculating the cost function. Okay, this is about the loss function and cost function of binary cross entropy loss. Let's see the advantages and disadvantages of binary cross entropy loss. Okay, the first advantage of this binary cross entropy loss is it is differentiable. Okay, it is differentiable. The loss function of this binary cross entropy loss is differentiable. Let me show you how this loss function looks like. Okay, let me quickly rub this. Okay, this is the, okay, this will be the loss function. Okay, this will be the loss function graph. Okay, this will be the loss function graph of binary cross entropy loss. Okay, it has multiple local minima in it, but it is continuous graph. Okay, it is continuous graph. So this graph is differentiable. When the graph is continuous, it is differentiable. So binary cross entropy loss is differentiable. Okay, it is differentiable. Okay, this is the best advantage of binary cross entropy loss. Now let's see the disadvantage of binary cross entropy loss. Okay, the main disadvantage of binary cross entropy loss is it is difficult to interpret. Okay, the interpretability of binary cross entropy loss is little bit difficult. Okay, as you see that it is a very big loss function. It is very big loss function. The one who sees it the first time will be little bit confused. So it is a little bit difficult to interpret. Okay, this is the first disadvantage of binary cross entropy loss. And the second and most important disadvantage of binary cross entropy loss is it has multiple local minima. Okay, it has multiple local minima. Okay, now this is the first local minima and this is the first local minima. Now when you apply gradient descent algorithm, okay, when you apply gradient descent algorithm on this loss function, what happens is the, okay, the gradient descent algorithm updates the weights and bias parameters and will always try to reach this global minima. Okay, it will always try to reach this global minima. Okay, once it is reached over here, once it is reached over here, it thinks that the work is over. Okay, the work is over. But when you observe the graph of this loss function, you see that there is another, okay, there is another local minima in this graph. Okay, there is another local minima in this graph. Okay, now you see that this, when you compare this both these points, okay, when you compare both these local minimas, Any one can be a global minimum. Okay, any one can be the least point where you get the minimum loss function, but your gradient descent algorithm will stop over here but will not go till here. Okay, this is the main disadvantage of binary cross entropy loss. Okay. In the previous section of the video, we have seen the entire intuition of binary cross entropy loss function, which is used for binary classification. Now, in this section of the video, we'll be seeing about the categorical cross entropy loss function. This categorical cross entropy loss function is used for multi-class classification. Okay, when you have multiple classes in your target variable. Okay, when you have multiple classes in your target variable, let's say you have dog, cat, lion. In this way, when you have more than two classes, two classes in your dataset, then we use categorical cross entropy loss function. Okay, categorical cross entropy loss function is used for classifying the multi-class classification. Is used for doing the multi-class classification. Okay, this is the loss function of categorical cross entropy loss function. Okay, loss function is equal to summation of j is equal to 1 to k, j is equal to 1 to k, yj log yj hat. Okay, summation of minus summation of j is equal to 1 to k yj log yj hat. Okay, this k determines the number of classes in your dataset. Okay, number of classes in your dataset. Okay, number of classes in your dataset. Okay, now if suppose you have three classes in your dataset. Okay, if suppose you have three classes in your dataset, then j will be running from 1 to 3 1 to 3, that is j is equal to 1 to 3 y1 log y1 hat is a first term, and the next term will be y2 log y2 hat. Okay, the next term will be y3 log y3 hat. Okay, in this way we'll be having the three terms. Okay, we'll be having three terms for the loss function. Okay, for the loss function. Okay, now if suppose you have n training samples, if you have n classes, if you have n classes in your dataset, j will be running from 1 to n. Okay, I hope you understood a little bit, but I'll be explaining you in detail about this loss function. Okay, about this loss function. Let's take an dataset. Okay, let's take an dataset that is nose, mouth, and eyes. Okay, these are the three features of your dataset. Okay, let's say these are the three features of your this is a sample dataset, and in this sample dataset we have three features. Okay, nose, mouth, and eyes. Now this is y. Okay, this is y. Okay, this is y, that is the target variable. Y is your target variable, and in this target variable we have three classes. Okay, in this target variable we have three classes, that is cat, dog, and lion. Okay, cat, dog, and lion. Corresponding to first training sample we have cat, and second training sample we have dog, and third training sample we have lion. Okay, these are the three classes of your dataset. Now after building our dataset, what we'll be doing, we'll be running our neural network. Okay, we'll be getting ready our neural network. Okay, now corresponding to that dataset, to make the predictions on that dataset, we'll be building a corresponding neural network with three inputs. Okay, with three inputs. First input is nose and mouth, and next is eyes. Okay, these are the three input features that will be given as input to the corresponding hidden layer. Okay, these three inputs are given as inputs to, these three input features are given as inputs to the corresponding hidden layer. And let's assume that we are building an three layered neural network. Okay, three layered neural network where you have two hidden layers. Okay, these are our two hidden layers. Okay, these are our two hidden layers, and this is our output layer. Okay, this is our output layer. Why we have three nodes in our output layer is we have three classes in our nodes. Okay, I have previously told you that the number of classes in your target variable determines the number of output nodes in your output layer. Okay, number of output nodes in your output layer. Okay, this is the corresponding custom neural network that we have built for the data set that we have taken. Okay, now for this neural network we'll be having some output. Okay, when our first training example is sent as input, when our first training example is set as input. okay, is sent as input. Now we'll be getting some predictions, right? We'll be getting some predictions for dog, so for cat, dog, and lion. Okay, now the first output node specifies cat, okay, class of the cat, and the second output node specifies the class of dog, and third output node specifies the class of lion. Okay, in this way we have three output nodes which specifies different classes. Now for this three output nodes we'll be getting three output predictions. Okay, we will be getting three output predictions. Let's say it is for cat we got around 0.5, and for dog we got around 0.2, and for lion we have around 0.3. Okay, you observe a pattern over here, the sum of these predictions, okay, sum of these predictions in the output layer is equal to 1. Okay, 0.5 plus 0.2 plus 0.3 is equal to 1. Okay, they add up to 1. Okay, in any neural network, when you are doing a multi-class classification, okay, multi-class classification, in the output layer, the sum of the predictions of the output nodes, is equal to 1. Okay, is equal to 1. So we have taken three different classes, and for these three different classes, when we add up these three different class predictions, it is summing up to 1. Okay, 0.5 plus 0.2 plus 0.3 is equal to 1. Now we have got our ready. Okay, we have got our predictions ready. Okay, we have got our predictions ready. Now these are our predictions. Okay, these are our y1 hat, okay, y2 hat, and y3 hat. Okay, these are our y1 hat and y3 hat, and y1 hat, y2 hat, and y3 hat. Okay, now for this corresponding data set we have built a custom neural network. Okay, and the custom neural network has outputted three different predictions for this first training example. Okay, now what we will be doing is, we'll be making some changes in this data, so that we can calculate our predictions. Okay, we can calculate our predictions. Okay, we can calculate our predictions. Okay, sorry, our loss function. Okay, we can calculate, sorry, we can calculate our loss functions. Okay, what are the changes? Okay, what are the changes? I'll be showing you over here. Okay, I'll be showing the changes that you will be making in your data set is when, okay, if you have a basic idea on machine learning, you might have known about the one hot encoding. Okay, one hot encoding is used for the nominal data. Okay, is used for the nominal data. Okay, we'll be having ordinal categories and nominal categories. Okay, in the categorical data we'll be having nominal categories and ordinal categories. Okay, in the ordinal categories, or in the ordinal categories, in the ordinal categories we'll be having the relationship. Okay, we'll be having the relationship between among the classes. Okay, relationship among the classes. Okay, instead of cat, dog, and the lion, if you have high, medium, and low, okay, instead of cat, dog, and lion, you have high, medium, and low as your classes. Then you apply ordinal encoder. Okay, ordinal encoding. Okay, ordinal encoding. Okay, how ordinal encoder works is, high is given the highest value, that is 2, and medium is given the middle value, that is 1, and the lowest value, the lowest value is given 0. Okay, in this way, when you have a relationship between, okay, when you have the relationship categories among the categories of your target variable, then you use ordinal encoding. If you have no relationship, okay, if you have no relationship, and each category, okay, each class in your target variable is are individual. Okay, here you see that there is no relationship between, okay, there is no relationship between cat, dog, and lion. Yes, there is no, we can't say that cat is high and dog is low. Okay, cat is high and dog is low, or lion is high and cat is low. Okay, so when you have this kind of data, where the classes are individual, okay, where the classes are independent of each other, then we use one hot encoding. How we do one hot encoding is, okay, first this target variable is transformed. Okay, first this target column is transformed into, okay, the rest of the columns are as it is, the rest of the columns are as it is, only this target column, okay, this target variable is transformed to cat, dog, and lion. Okay, in this way we have transformed our target column to three different classes. Okay, three different classes, and each class, okay, each class will be having an value. Okay, let's say for cat we are having 100, dog is represented by 1010, and lion is represented by 001. Okay, okay, first what we have done is, we have taken, we have divided our target variable, into different columns. Okay, as we have three different classes in our target variable, we have divided into three different columns. Okay, if you have four different classes in your target variable, another column is added over here. Okay, another column is added over here. Okay, now we have three different columns where cat represents. Okay, to represent cat we'll be using 100, to represent dog we'll be using 010, to represent lion we'll be using 001. Now let's take for the cat. Okay, for cat is represented by 100. Okay, cat is represented by 100. Okay, these are the true output. Okay, this is the true output. Okay, this is y1, this is y2, and this is y3. Okay, this is y1, this is y2, and this is y3. Now let's say this first this first chain gate, sorry, now, this first training example is sent to our neural network that we have built previously. Okay, this first training example is sent to our neural network that we have built previously, and it has produced an output of 0.5, 0.3, and 0.2. Okay, for this first training example, the true output is cat. Okay, for this first training example, the true output is cat. How we represented the cat? By using the one hot encoding 100. Okay, 100. In this 100, this represents y1, this represents y2, and this represents y3. Okay, now when you send this into your custom neural network, when you send this first training example to your custom neural network, these are the corresponding predictions. Okay, you have three output nodes, right? Our first node has outputted 0.5, our second node is outputted 0.3, and third node is outputted 0.2. Okay, this is y1 hat and y2 hat and y3 hat. Now what you will be doing is, for calculating the total loss function, what you will be doing is, you will be taking first. Okay, you will be taking, now you will be expanding your, terms based on the number of classes. Okay, you will be writing first y1 log y1 hat. Okay, y1 log minus y1 log y1 hat. I don't have space over here, that is why I'm not writing. Okay, first our first term will be minus y1 log y1 hat minus log y2 hat. Okay, minus y2 log y2 hat, and our next term will be minus y3 log y3 hat. Okay, in this way we'll be having three terms, and you'll be substituting these corresponding values. Okay, you'll be substituting these corresponding values. Okay, now these are our y1, y2, y3. Okay, for our cat label, okay, for our cat class we have three different predictions. Okay, these are the, sorry, our cat class is represented by 100, where 1 is represented by y1, 0, y2 is represented by 0, y3 is represented by 0. Okay, now for the cat, now for the same cat class, these are the predictions. Okay, these are the predicted outputs, where 0.5 is y1 hat, 0.3 is y2 hat, and 0.2 is y3 hat. Okay, 0.5 is y1 hat, 0.3 is y2 hat, 0.2 is y3 hat. Okay, in this way you substitute these values in this loss function, and you determine the overall loss function of your categorical cross entropy. Okay, this is just an sample. You can take any data, apply one hot encoding. Okay, apply one hot encoding. These features remain the same, but only these, okay, but only the classes in the target variable are transformed in this way. Okay, are transformed in this way, and these are the, okay, like that. In for individual classes, we'll be having individual values, corresponding predicted values, for calculating the loss function. Okay, this is the overall loss function for categorical cross entropy. Okay, now let's determine the cost function. Okay, now let's determine the cost function. Cost function is represented by minus 1 by n. N represents the number of training samples. Okay, number of training samples that we are considering to calculate the cost function. Okay, summation of I is equal to 1 to n, and summation of j is equal to 1 to k, and yij log yij log y1, sorry, yij hat. Okay, true output and predicted output. Okay, now let's take an example. Let's say we have Okay, now we have three training samples, right? Okay, we have three training samples. Now what we'll be getting over here, minus 1 by 3 summation of I is equal to 1 to 3, I is equal to 1 to 3. Okay, and summation of j is equal to 1 to 3. Okay, as we are having three different classes, summation of j is equal to 1 to 3. Now our first term will be y 11 y11 log y11 hat. Okay, y11 log y11 hat, and our next term will be y12 log y12 hat. Okay, y12 log y12 hat. Okay, this y11 and y11 hat are, this is our y11 and this is our y11 hat. Okay, now y12 and y12 hat. Okay, this is our y12 and this is our y12 hat. Next term is y13 and this is y13 and this is y13 hat. Okay, now this is for the first training sample. Now when it comes to second training sample, this is your corresponding true output. Okay, this is your corresponding true output. And how you determine that the second cost loss function of the second training sample is y21 log of y21 hat and y22, okay, minus y22 log of y22 hat and y23 log of y23 hat. Okay, this represents us, okay, this represents y21 and this represents y22 and this represents y23. Okay, this represents y31, y32 and y33. When you have corresponding predictions, you can put over here and you can calculate the entire cost function of these three training samples. Okay, this is the loss function and this is the cost function of categorical cross entropy. N determines the number of training samples, j determines the, okay, j to k, okay, j to k determines the number of, classes in your target variable. Okay, classes in your target variable. Okay, this is the entire intuition of categorical cross entropy. Okay, hope you like this video. If you like the video, please like, share and subscribe. Thank you.